Good morning, and thanks Eric for the introduction. Welcome to my presentation on routing optimization for delay-tolerant networks in rural scenarios. This is the outline of my presentation. I will start with the introduction on the subject and show you the problem I am addressing on this presentation, some previous unrelated work, the methodology I am using for this research, proposed solution, and some of its results. Finally, I will draw some conclusions and show you some of the future work I'm working on. So let's start. Delay disruption tolerant networks are a new kind of network, a new technology that was created originally from satellite communications with the idea to create an interplanetary network to connect satellites from Earth with satellites in other planets like Mars, or spatial missions to Mars or to the solar system. So initially those satellites and those missions had a direct link with Earth. The idea was to create a network so they can have some reliability and some alternative paths for the communication. So this started in NASA, but this network could not work with the protocols and information we have of current networks, since we have very long distances in space. um, the protocols won't work. To Mars, for instance, we can have 8 minutes delay when Mars and Earth are close, and 40 minutes of delay when Mars and Earth are farther away. So with these times, most protocols based on TCP will not work, and then we had to invent new protocols. So this is delay and disruption tolerant networks. Those networks will experience long and variable delay. We are talking here about hours or days. We will experience frequent partitions, so nodes can become isolated, or parts of the network can become isolated. Also asymmetric data rates. As in satellite communications, we usually send more data towards Earth than we send to the satellite, and high error rates for these same characteristics. However, since those spatial applications at the beginning of this technology, we have evolved to earthly applications. So on Earth, we can use this same technology to battlefield communications, to wireless sensor networks in isolated regions, and more importantly, to bring internet to people in isolated communities or underdeveloped regions. So we are focusing here on this application on delay tolerant networking for rural scenarios, where we can use this technology to bring internet to people. Basically, as of now, 40% of the world population has access to internet, according to the ITU, and also internet connectivity is a way to help people in underdeveloped regions to get out of poverty and close the digital divide and economical divide. So this is our main application, and this is the scenario we have in mind. The technical question we are trying to solve is how to deliver messages from these small towns to a node that can connect to internet and give them back their answers in a delay tolerant networking scenario where the answers can take hours or day to come back. So we will be using the availabilities of the paths, but with the probability of this availability. So we call it the availability probability of each link, and when we multiply all these availability probabilities of the links, we will have the availability probability of the paths. And we want to find the paths with the best availability probabilities. Some previous unrelated work are the ITU statistics I mentioned before. They give very good examples of how internet and internet connectivity can help poor communities become more organized and help them close the economical divide in education and information. Also, here in the references are some very good references about the delay tolerant network architecture proposed for these spatial applications initially. The most important are RFC 4838 from 2007 and RFC 5050 from 2007 also. There are also some very good reviews about delay tolerant networks and some implementations for rural applications. DACnet and Tire are one of the most famous applications of this technology for rural connectivity. So the methodology for my research is as follows. I am proposing a scenario. This scenario has some characteristics and brings some constraints with it. We will model this scenario with the objective function in mind, that is, find the best paths in the network. So we will use a mathematical model for this. We'll solve this mathematical model. Then we will propose a distributed algorithm that can be implemented in the nodes with local information. We have to remember that the mathematical model will have all the information in the network, and the distributed algorithm will only have local information. Then we will simulate the distributed algorithm, and finally we will show some results and draw some conclusions from it. So the solution proposed here is a mathematical optimization model that takes into account the availability probabilities of the links that will make the paths in the network, and the mathematical model will have all the information of the network for all time. We are also proposing a decentralized forwarding algorithm where nodes will only have local information, and they will have to take decisions on where to send the packet, or if they should store the packet until a better availability probability, a better neighbor with a higher availability probability will show. So those are the decisions we're making here. So this is how it works. We have a network, and in this network we have some nodes that want to send information to internet. There is a node connected to internet that will be the destination, and we want to send the information to that node to eventually retrieve some answers. So the nodes here can see their neighbors and can know the availability probabilities of the links to their neighbors, and we want to decide uh, the paths to send the information from the sources to the destinations through time. We have to take into account that the availability probabilities will change through time since the nodes can be moving, and we are modeling this movement with the availability probability changes. So we have a packet from node 1 to node 6 in this scenario. We are checking all availability probabilities in the network, so we can choose the best one and send the packet to node 2. Then node 2 will check the best availability probabilities available to him and will send the packet to node 5, and finally node 5 will send the packet to the destination. So in the mathematical model we have all this information, and since the availability probabilities changes through time, we are expanding the initial graph to a graph with all availability probabilities through time. So it's a bigger graph that has all the changes, and we will find the path from node 1 to node 6 through any time. We will find the best path available. So the mathematical optimization model takes into account the availability probabilities and the information flow through the links and multiplies it to find the best availability probabilities. But since this is a nonlinear optimization model, we are using a linear approximation using the logarithm, and then we sum the logarithm of the availability probabilities multiplied by the information flow, and we have some constraints that will assure that the information demands are met, like the nodes who have information to send can send it to the destination, and we also have a constraint that keeps the information flow below the capacities of the channels and the buffers. And finally, there is the constraint that the flow should be positive and integer. Our heuristic, by the other hand, is based on local information, so each node has the information of the availability probabilities of the links to their neighbors, and it chooses the best one and compares it against a parameter called alpha. So if the better availability probability is bigger than alpha, the node will use that link to send information. In this case, it sends information to node 2 at time 0, and at time 1, node 2 evaluates all availability probabilities and check it against alpha. So you can send the packet to node 5, and in node 5 the node checks the availability probabilities, and the best one is less than alpha. So the node will have to store the packets in its buffer and wait until next time to check again and find a better availability probability, in this case bigger than alpha, and will send it towards the destination node. This is the pseudocode for the forwarding heuristic. There is the parameter alpha against which should check the availability probabilities. From this distributed algorithm, we run some simulations um, for scenarios from 6 to 10 nodes, thinking in this rural connectivity application. So we change parameter alpha from 0.1 to 0.9, and every node in the network will send a packet to the last node. So those are the scenarios. We choose them to show like a small town organization, but it can be random, and we had some results with random too in other work. Um, Here are the results. So we can see the dotted line at the bottom is the hop count. We see that this doesn't change with alpha. Um, we also see the dashed line is the availability probability, and the continuous line is the time steps used for to find the destination. So we can see that the availability probability increases with alpha, and also the time to deliver the messages increases with alpha. So this is for 6 nodes, this is for 7 nodes, we can see the same behavior, and for 8 nodes we can see the same behavior here. So what we see is that for alphas between 0.8 and 0.9, the increase is exponential, both in availability probability of the paths and in time steps to deliver the messages. So we are recommending to choose an alpha between 0.6 and 0.7, since this alpha will show an increase in availability probability, but with a lesser increase in time. So although those networks are delay tolerant and can take hours or days to deliver and receive messages, we want to use that time efficiently. So we want to reduce the time as much as we can, and that's why we are choosing alpha between 0.6 and 0.7 that will minimize the time steps but increase the availability probabilities of the paths. So this is my presentation. We are working on the nonlinear model for future work, and also in creating a history of contacts between nodes, so we can choose the nodes that will connect to the destination more likely, and that it's for future work. So thank you for listening. Here are some references. If you have some questions, please write me at ce.velasquez917 at uniandes.edu.co. Thanks.